Hi guys, we're going to go through the Unit 7 exam short answer, which starts right here. So let's read what we have here. Okay, a 5-gram sample of liquid ammonia. I'm going to highlight 5-gram ammonia, so remember that's not water, is originally at 210 K. Alright, that's a temperature. I'm going to pay attention to that. The diagram of the partial heating curve represents the vaporization of the sample of ammonia at standard pressure due to the addition of heat. Heat is not at a constant rate. I'm going to go back up and highlight vaporization because when I see that, I know that this partial heating curve, if I look down, this must be going from a liquid to a gas. So that's going to help me a little bit. And it says that it gives us some physical constant in the accompanying table. So I'd go down to this table and I would look and I'd say, okay, it's ammonia. I'm going to want to use these. So that means that I can't use table H. So describe what is happening to both the potential energy and the average kinetic energy of the molecules of the ammonia sample during time interval BC. Your response must include both potential energy and average kinetic energy. So I'm looking between here, these two. I'll highlight them. I'm going from here to here. So really I'm focused on this line. And what I want to notice is that temperature here is constant. So my kinetic energy is constant. And if the potential energy is, or kinetic energy is constant, sorry, that means potential energy must be changing, and since this is heating curve, that means my potential energy is increasing. So the answer to A, I would say this. Kinetic energy is constant, potential energy is increasing. Again, it's a heating curve, so it's increasing, and kinetic energy cannot change without temperature. B says, space on your answer sheet, calculate the total amount absorbed by the 5-gram sample. So total heat, that's Q. 5-gram sample, it's ammonia. During time interval AB, okay, I'm going to focus there. I have to include both the numerical setup and the calculator result. So I'm actually going to go right to my answer sheet here. And actually, I can just fill in the last question. Potential was increasing, kinetic was constant. And we're going to show them our setup. So they want the heat of the 5-gram sample, remember, at interval AB. So let's go back up. AB is right here. Okay, AB. So when I'm looking at A to B, I'm noticing that this temperature is changing. So I'm focused here. So I do have a change in temperature, so I'm going to go ahead and set up MCAP. Q equals MC delta T. So let's plug in my M. Go back to the problem. Sorry here. 5 grams. Specific heat, I'm going to go to my chart. Specific heat capacity of NH3 is 4.71. And my change in temperature, I'll do it on the side, my change in temperature was my final minus my initial. So the highest temperature, if we go back, 240. Lowest temperature was 210. So 30 was my change in temperature. So I'm going to go ahead and plug in 30 right here. And I'm going to go ahead, I don't have a calculator. I'll use my phone here. So I've got 5 times 4.71 times 30, I get 706.5 joules to keep my units. Okay, so now we're on to question 22. It says, on the answer sheet, calculate the heat released. All right, I'm going to highlight what's important. Heat released when 25 grams of water freezes at 0 degrees Celsius. So I like that word freezes too. So I'm going to go back and I'm going to look, okay, what equation do I want to use? Well, Heat released is Q. Here's my mass. I know it's water, and it freezes. That's a keyword telling me use HF. So I'm going to go to my answer sheet because it says to show the setup and get the answer. So I'm going to use Q equals MHF. I know that my mass was, go back, 25. And my heat of fusion, that is a constant. Coming in on table B. Table B, heat of fusion for water is 334 joules per gram. 334. So again, I'm going to plug into my calculator. You should do the same. 25 times 334. And we're going to get 8,350. Correct unit would be joules because we solved for a heat. On to question 23. Naphthalene, a nonpolar substance that sublimes, ooh, that's probably a key word, at room temperature can be used to protect wool clothing from being eaten by moths. Explain in terms of intermolecular forces why naphthalene sublimes. Well, first I want to think, what the heck is sublimes? Sublimes is sublimation. And we know that sublimation is when I go from a solid to a gas. So I want to think in terms of solids would have strong intermolecular forces. Gases would be weak. Let's write that. So strong IMF, weak IMF. So if I start strong, all of a sudden I'm weak. That means the intermolecular forces overall for naphthalene should be pretty weak. So we will say weak IMF. Remember, the least words that you write is always better. So naphthalene has weak intermolecular forces. Question 24. Base your answer on the information below in the accompanying table. Okay, sorry, just let me get it all set so you can read it with me. Substance is solid at 15. A student heated a sample of the solid substance and recorded the temperature in 1 minute interval in the accompanying table. What is the evidence that the average kinetic energy of the particles of the substance is increasing during the first 3 minutes? So I'm going to go back over. Let's look closely at the first time here. First 3 minutes. And let's remember that average kinetic energy really is just temperature, because the definition of temperature is the average kinetic energy. So I look here and I see the temperature was 15, then 32, 46, 53. So the temp is increasing, and that's exactly what I want to put on my answer sheet. So I'll go back here and I'll say temperature is increasing. Okay, so on to 25. Okay, sample of helium gas is in a closed system with a movable piston. The volume of the gas sample is changed when both the temperature and the pressure of the sample are increased. The accompanying table shows the initial temperature, pressure, and volume of the gas, as well as the final temperature and pressure of the sample. So, okay, I have initial temperatures, final temperatures, initial pressure, final pressure, and a initial volume. So A, space in your answer sheet. Oops, sorry, a little space here. Go over here. Show the correct numerical setup for calculating the final volume of the helium gas. So I want to look, and what I'm noting is I have a T1, I have a T2, I have a P1, I have a P2, I have a V1, and I'm finding a V2. So if I want to look, I go to my answer sheet, reference table. I'll notice the combined gas law, P1 times V1 over T1 is P2 times V2 over T2. So I might as well go to my answer sheet. To do my setup, I'll say, let me move this so I can look at my variables. We have, oh, let's write our equation. P1, P1. Oops, sorry. Yep, nope, that's not it. Beep. P1 times V1 over T1 equals P2 times V2 over T2. If I plug in those numbers, I'm going to go ahead and put 2.0 as my P1. My V1 is going to be 500. And I'm getting this from my table. Over initial temperature, it is in Kelvin. That's perfect. I don't have to change anything. Remember, it has to be in Kelvin. Equals P2 is 7.0. V2 is X. And T2 is... Oh, you didn't even tell me. I messed up my temperature. 200 was my initial temperature. 300 was my final temperature. So now we have our setup. I actually don't like that. Let's rewrite it one more time. 2 times 500 over 200 equals 7 times X over 300. Sorry for the confusion. It's a little better. That's what I want to see. So now it says, convert the final temperature of the helium gas to degrees Celsius. So I want to think, I don't care at all about the equation that I just did. I now just want to look at the final temperature of the helium, which was 300. So I'll think, okay, I'm going to convert to Celsius. I'll do my work right here. Celsius plus 273 is my Kelvin. There's my equation. If I'm not sure of that, I can go to my reference table and notice right here, temperature. Sorry, get my shadow out of the way. I mess with the light a little bit here. It's kind of sunny. There we go. So K plus degree C is plus 273. So I say no, my K was 300. My Celsius, I'm finding it, X plus 273. So we'll subtract 273, subtract 273, and you're going to get 27. So I'll go to my answer sheet and write in 27. Okay, 26. Base your answer on the diagram, which has a piston confining gas and a cylinder. On your answer sheet, oops, sorry, we skipped this. The gas volume in the cylinder is 6.2 milliliters. Its pressure is 1.4 atmospheres. The piston is then pushed until the gas is the volume of 3.1 milliliters, and the temperature remains constant. That sounds a lot like I should be grabbing some variables here. So I see milliliters. Milliliters I know is a volume, so I'm going to call it an initial volume. I also see atmosphere, so that's a pressure. And then I have another volume, must be V2. Temperature remains constant. So remember, I can go to my combined gas law right here. And if temperature is constant, I just put my finger over it. I just take it right off. So I get P1 times V1 equals P2 times V2. So I know that's actually probably what I'm going to do. So let's see what question asks us to do that. A, on your answer sheet, calculate the pressure in atmospheres after the change in volume. Show our work. So let's just go back to our answer sheet. We'll show our work here. Our setup, we decided it had to be P1, V1 is P2, V2, because we have temperature that's constant. My P1, 1.4. My V1 is 6.2 equals your P2 is, oh, that's what we're finding. Sorry, that's X. And our V2 is 3.1 milliliters. And so this is what I would be looking for work right there. And then B says record our answer. So I'm going to go ahead, I'm going to get that. We go 1.4 times 6.2 equals, now I'm going to divide that by 3.1. So I'm going to get 2.8, and we should put a unit on that. I solve for pressure, so ATM. 27. Airbags are an important safety feature in modern automobiles. The airbag is inflated in milliseconds by an explosive decomposition of NaN3. The decomposition reaction produces N2 gas as well as Na solid according to the unbalanced equation below. When the airbag inflates, the nitrogen gas has a pressure of 1.3 atmospheres, a temperature of 3.01 K, and a volume of 40 liters. In the space in your answer sheet, calculate the volume of nitrogen gas at STP. Your response must include both numerical setup and the calculated volume. So let's see what they gave us in the problem. I've got some room to write above, so I will. So I see 1.3 atmospheres, that's a pressure, so P1 is 1.3 ATM. T1 was 301 K. And I have over here, I had 40 liters. So that must be my volume. So V1 is 40 liters. And now they're telling me I want to calculate the next volume. So we'll say V2 is question mark. And they tell me it's at STP. So remember, you can always go to table A to get STP, standard pressure 101.301 ATM. Our temperature, we're always going to use that Kelvin for our gas laws. So I know that my P1, let's do atmospheres, 1 ATM. Oh, sorry, P2. And T2 is going to be 273 K. They, again, want us to calculate, and they want the numerical setup and the right volume. So we'll go to our answer sheet. For our setup, I'm going to go ahead and use the entire combined gas law because I have 5 of the 6 variables. So I have P1 is 1.3, V1 is 40 over T1, 301 equals, now I have a pressure of 1, a volume of X, and a temperature of 273. We're going to go ahead and plug that in our calculator. Remember, we're just going to cross multiply in order to get that. But again, in your setup, I really don't want to see the cross multiplication, but just to show you. And I'm going to go ahead and plug that in. I'm going to do it stepwise. So I get 1.3 times 40 times 273. 14,196 divided by what would be 301 times 1. So 301 divided by 301. And I get 47.2 if I round it. I don't think, no, you can't see it on my phone, but it's 47.162. 7. So I decided to just go with 47.2. And I need to put a unit, so we're going to go milliliters. Ooh, should I check back? Am I right? Am I wrong? You should be saying, you're wrong, you're wrong. It's in liters. So I'll go back and say, nope, it's liters. Boom. So now, moving on, we're almost there. A little bit more. 28. Given the balanced equation for dissolving NH4Cl in water, see accompanying diagram. A student is holding a test tube containing 5 milliliters of water. When the sample of NH4Cl is placed in the test tube feels colder to the student's hand. Describe the direction of heat flow between the test tube and the hand. You want to always remember that heat goes hot to cold. So if the test tube feels colder to the student, then that means the hand was warmer. So the hand is your hot, and the test tube is your cold. We'll put that on our answer sheet, which I have right here. So heat will transfer. Sorry, it's typed funny. And the light, it's an actual sunny day. Can you believe it? So hand to test tube. Boom, question 29. Heating curve. See if I can just write everything here. Might be easier. So I have a cooling, starting as a liquid above the freezing point. I want to note that that's a liquid, so this must be a solid. So which line segment represents a phase change only? So remember that phase change, that's our key, what we're looking for. Phase changes are going to happen right here. They always occur on our flats of our graph, our flats. So our phase change, I would want you to say here, BC would be your answer. What is the melting point of lauric acid? Well, right here when I'm looking, I have a liquid, I have a solid. B would be the very first point that I would see a solid, that would be my freezing point. So C must be my melting point because, again, I kind of read it backwards. But remember, they don't want you to give a point. They want you to give the temperature. So I'd go here and say, there's about, I'd say anywhere between, I'd go like 45 degrees Celsius, plus or minus 2. Now, in C, at what point do the particles of lauric acid have the highest average kinetic energy? Remember, that is temperature. So I want the highest temperature. So I'm going to look. It was highest at 60. So point A is our answer there. And D, name the phase change that takes place during this 10-minute cooling time. Well, they told us, again, up here, it was starting as a liquid. Sorry, can you guys even see that? It's so bright. So bright. Why? It's too sunny. So I'm going from liquid to solid. I want to name what that is. So if I write it over here, I am freezing or solidifying. And that would be your answer there. Okay, we gotta hurry. We're losing the light. It's too bright. It's too bright. Okay. So, 30. Last one. Explain why the number of molecules in N2 Y is the same as the number of molecules CO2 in cylinder A. Well, this is Avogadro's law. I look, same volume, pressure, and temperature, same volume, pressure, and temperature. These are the same. So, I would say it is Avogadro's law. But I want you to describe what that means. So I would say they have the same volume, temp, and pressure. Boom. Answer to A. B. Last question. Woo! So exciting. So let's see. Square it up here. The temperature of the CO2 is increased to 450 K. That increased to, must be a second temperature. And the volume in cylinder A remains constant. On your answer sheet, show the correct numerical setup for calculating the new pressure. So I'm looking for a P2. So again, I'm going to look and say, which equation am I going to want to use? Well, I have a temperature and I have a pressure. My volume's constant. So go here. Boom, can you see that? So I take out my volume. Can you see that? No, probably not. Here, I'll do it over here. No, you can't see it. But here, look. Volume's gone. Volume's gone. That means I've got P1 over T1, P2 over T2. That's the equation. Let me write it here. Let's go ahead and plug it in on our answer sheet so we can show our setup. My initial temperature, remember we're talking about cylinder A, so my initial pressure was 1. My initial temperature was 300. So 1 over 300 equals new volume, or new temperature, sorry, volume's constant. New temperature, 450. I'm solving for my pressure. So it's X. There's your setup. You don't even have to solve it. So thanks for watching, guys. See you soon.